Welcome to this lecture on methods in biostatistics. Today, we are going to explore the measures of central tendency, specifically the mean, median, and mode. When we collect biological data, whether it is the heart rates of patients or the number of bacterial colonies in a petri dish, we often end up with a massive pile of numbers. To make sense of this data, we need a way to find the center, or the typical value that represents the entire group. That is exactly what these three measures help us achieve. Let us begin with our first measure, the mean. Imagine you and your friends are sharing cookies, and you want to be perfectly fair. You would pool all the cookies together and divide them equally. This simple act of pooling and sharing is exactly what the mean represents in statistics. It acts as the mathematical center of gravity for a set of numbers. Because it incorporates every single data point into its calculation, it provides a comprehensive overview of the sample. However, this also means it is highly sensitive to extreme values or outliers. If one patient has a drastically different heart rate, the mean will be pulled toward that extreme value. Now that we understand what the mean is conceptually, let us look at how it works mathematically. The formula for the sample mean might look complex, but it is actually very straightforward. It comes from the idea of summing everything up and dividing by the count. The symbol x bar represents the sample mean we are trying to find. The Greek letter sigma tells us to add up all the values, while x sub I represents each individual data point in our set. Finally, the letter n stands for the total number of observations. If the total number of observations increases while the sum stays the same, the mean will decrease, because the total is being spread thinner across more individuals. Before we move on, let us see this with a concrete example. A nurse measures the resting heart rates of 5 patients, which are 72, 76, 74, 81, and 77 beats per minute. We are asked to find the mean heart rate to understand the group's cardiovascular baseline. We chose this formula because we have a simple, ungrouped list of numbers. First, we find the total sum of all the heart rates by adding them together, which gives us 380. Next, we divide this total pool of beats by the number of patients, which is 5. This gives us a final calculated mean of 76. Physically, this tells us that if every patient had the exact same heart rate, it would be 76 beats per minute, indicating a healthy average. This formula we just saw works perfectly for small lists, but this brings us to an important question. What if we have massive amounts of data? In biological sciences, data is often grouped into frequency tables rather than listed individually. When data is grouped, we cannot just add the unique numbers together. We must account for how many times each specific number appears, which is called its frequency. To find the true center, we have to multiply each value by its frequency to find the total for that specific group, and then sum those totals. This ensures every single observation is still fairly represented in the final average. Now that we understand the need to account for frequencies, let us look at the mathematical form of this concept. This formula is a direct extension of the basic mean, adapted for grouped data. Here, f sub I represents the frequency, or how many times a specific value occurs. The variable x sub I represents the value itself. The numerator tells us to multiply each value by its frequency and add those products together, giving us the grand total. The denominator is the sum of all frequencies, which is simply the total number of observations. If a particular value has a very high frequency, it will pull the mean closer to itself, heavily influencing the final average. Let us apply this grouped formula to a real scenario. A biologist counts bacterial colonies. 2 dishes have 10 colonies, 3 have 15, and 5 have 20. We need to find the mean number of colonies per dish. We use the grouped formula because our data is organized by frequency. First, we multiply each dish count by its colony count to find the total colonies for each group, giving us 20, 45, and 100. Adding these together gives a grand total of 165 colonies. We then add the frequencies to find there are 10 dishes in total. Dividing 165 by 10 gives us 16.5. This means a researcher can expect to find about 16.5 bacterial colonies on any given petri dish in this batch. So we have thoroughly explored the mean. This brings us to our second measure of central tendency, the median. Imagine lining up students from shortest to tallest and picking the person standing exactly in the middle. That is the median. It is formally defined as the middle value in a dataset when the values are arranged in order. Unlike the mean, the median is a positional average rather than a mathematical one. Because it only cares about the middle position, it completely ignores the actual numbers at the extreme ends of the data. This makes it an incredibly robust statistic when dealing with skewed distributions or extreme outliers, like a patient who stays in the hospital for a year when most stay for 3 days. Now that we know the median is all about position, let us look at the formula used to find that position. It is important to note that this formula does not give you the median itself. Rather, it tells you the exact address of the median in your ordered list. The variable p represents this position. The variable n represents the total number of observations. By adding 1 to n and dividing by 2, you find the rank where the middle value lives. If your total count, n, increases, the position p will shift further down the list. If n is an odd number, this formula points to a single middle data point. If n is even, it tells you to look exactly halfway between the two middle numbers. Before we move on, let us see this positional formula in action. A researcher records the recovery times for 7 mice: 4, 2, 7, 5, 9, 3, and 4 days. We need to find the median recovery time to understand the typical experience, avoiding the skew from the mouse that took 9 days. The absolute golden rule here is that we must sort the data first. We arrange the times from shortest to longest: 2, 3, 4, 4, 5, 7, and 9. Since we have 7 data points, we plug n equals 7 into our formula, which gives us a position of 4. We count to the 4th number in our sorted list, which is 4. This tells us exactly half the mice recovered in 4 days or less. Now that we have mastered the mean and median, let us look at our final measure, the mode. Imagine you manage a cafeteria and want to know which soup to make. You do not care about the mathematical average, you just want to know which soup sold the most. That is the mode. It is defined as the value or category that appears most frequently in a given dataset. Unlike the mean or median, the mode does not require any complex calculations or ordering of data. You simply count the frequencies. It is uniquely important because it is the only measure of central tendency that can be used for qualitative or categorical data, like blood types or eye colors, where numbers are not involved at all. Because the mode is a concept of frequency rather than arithmetic, its mathematical representation is incredibly simple. The formula simply states that the mode, represented by m sub o, is equal to x sub max. Here, X sub max represents the specific data point or category that corresponds to the maximum frequency in your tally. There's no division or summation involved. If the frequency of a specific category suddenly surges, that category will overtake the others and become the new mode. It is also worth noting that if two different values tie for the highest frequency, both are considered the mode, making the dataset bimodal. Let us see how we apply this to categorical data. A geneticist records the eye colors of 15 fruit flies, noting down red, white, and brown. We need to determine the modal eye color to find which genetic trait is most expressed. We choose the mode here because eye color is a category, so mean and median are impossible to calculate. Our strategy is to create a simple frequency table. By carefully counting, we find that red appears 8 times, white appears 4 times, and brown appears 3 times. Since 8 is the highest frequency, red is our mode. This tells the geneticist that the red eye trait is the most frequently expressed phenotype in this specific population. Now that we have calculated all 3 measures, let us look at how they interact visually. What you're seeing here is a right-skewed distribution curve. The horizontal axis represents the values in our dataset, and the vertical axis represents their frequency. Notice the highest peak on the left? The dashed line dropping from this peak is the mode, because it represents the most frequent value. As we move to the right into the long tail, we see the median, which splits the data exactly in half. Finally, furthest to the right, we see the mean. The mean has been pulled away from the peak by the extreme values in that long tail. This diagram perfectly illustrates why we must choose our measure carefully depending on the shape of our data. We have covered a lot of ground today, so let us summarize the most important ideas. First, the mean is your mathematical balance point, incorporating every piece of data but highly sensitive to outliers. Second, the median is your positional center. By simply finding the middle of an ordered list, it cuts through the noise of extreme values. Finally, the mode is your popularity contest, serving as the ultimate tool for categorical data, where numbers do not apply. Understanding how these 3 measures connect and differ gives you the power to accurately summarize any biological data set you encounter. You now have a solid foundation in central tendency.